So you may know how to differentiate the linear equation and non-linear equations. In common tongue, we used to say that it's easy to just evaluate the roots by for the cases linear equations. But when it comes to the non-linear equation, is a bit tedious, and it has to be, you have to adopt some numerical approach or numerical method in order to determine that the roots. Okay, so this is one of them. So this is what we're going to discuss in the chapter 4. So we're going to study about several algorithms which is we use in order to determine the root of for the nonlinear equations. Okay, so the arrangement of the method I list down based on that from low order to high order. Okay, the bisection method today we're going to discuss is considered is our low order scheme, which is we use in order to determine the roots. So in the following lessons, we're going to slightly high order, and it's more complicated, and it's also like, we use in order to determine that roots. Okay, so you can see that the trends, how does it work from low order to high order. Okay, for basically you should understand that what the difference between, you may ask, like, why don't you just use the low order, because still got answers. Okay, correct, but the accuracy is like we lost. But same time, remember that if you tend to use that high order approaches, high order numerical approaches in order to determine the roots. So one is we have to consider the computational complexities. So at the moment when you use the high order scheme, so what will happen? The method will tend to, it will become complex. It's become more complex. Okay, the number of arithmetics in order to calculate it will be higher. Okay, like addition properties or subtraction properties, multiplication and division properties. So it's the complexity will be getting higher and higher. All right, when you go for high order scheme. All right, for the low order scheme, it does not require that much, but you will take the number of iteration a lot. So for example, if say you use that bisection method, so if you can get 10 iteration, then you will get answer. But if you use the high order scheme, you just only require 3 or 4 iteration, you only got the closer point. So that's the idea. Okay, so there is a pro and cons. All right, so pro and cons. So if you use that low order, definitely it will take a huge number of iteration, higher number of iteration, and as well as it will take, consuming time. Okay, number 2 is it will consume your times, and number 3 is also it affect that accuracy. But the accuracy you can improve by adding that number of iteration. That is the relation between accuracy and number of iteration. But when we consider high order scheme, so as I said earlier, it will be more complex. The calculation will be more complex, but the beauty is it will be converged very fast. All right, so it will just 2 or 3 or 4 iteration or 5 iteration, you give that the accurate solution. Okay, that's the differences. Okay, now today we're going to discuss about bisection method. Okay, today content will be, we're going to discuss about the root finding algorithm, and then we're going to discuss about what the theorem of that bisection algorithm, and then we will discuss in deeper the bisection steps, step-by-step approach, and then we also discuss about what is the disadvantage of the bisection. Okay, what is the drawbacks lies behind in the bisection approaches. And then we discuss about what is the stopping criteria we have to fulfill in order to we get that final solution of bisection method. And then we do some application. So application of bisection method in the nonlinear problems in order to determine their roots. Okay, so after you studied, you'll be able to and know how to apply and solve a root finding by using the root finding algorithm. And then you also know how to use that bisection algorithm. Okay, now root finding algorithm. So we go precisely. Please, guys, if you don't get it, make sure you ask me. I will teach step by steps. All right. So don't keep it, okay, silence. Make sure if you don't get it, please, you can put up your hand, or maybe you can leave your message in the chat box, or maybe you can turn it on in your audio. You can ask me the questions. All right. So every section, once I finish, I will ask, and then make sure you respond accordingly. So I will give you that clear explanation so that you can grasp that the concept. Okay. Now, root finding algorithm. Let's pop the hood now. Root finding algorithms or root finding aims to find that the zeros, okay, the zeros of that the given mathematical function. Okay. All right. So just we find that we approximated any value, we start from the zeros. All right. If they approximated zeros. All right. Fx function s2 equal to 0. So that's what we call like it's a zeros of given mathematical function. So that's that one technique we use in that the root finding algorithm. Root finding algorithm is a numerical method based on the iterative process. Okay. So in common tongue, so when we say that root finding, so in a linear, we just use that, you know, we straight away you can get the exact solution. But in numerical methods, usually what we do, so we just, in order to find that the approximation solution or approximation roots, so you had to done a few iteration process in order to get a accurate, you know, accurate roots where the line pass through at that x-axis. Okay. Okay. Let me just show you that. Okay. All right. So let's say this is your graph. All right. So what happened? Say this is a graph. So this say is passed through. So this point. So you pick any point, you just give an initial guess. Once you make initial guess, so you need to approximate until, okay, every iterative process, the root is come closer to that the point when the line is cut through. Okay, so that will be in the process. That's what they say. The root finding algorithm is numerical, which is that numerical approach, and it's take over by the iterative process. Okay. Okay. Root finding method for high order function, we can classify into the two methods. One is we call as a bracketing methods. Okay, so bracketing method, the one we learned, all right, right now, the bisection method. And another method is open methods. Okay, open methods. So these are two methods we usually use in order to determine that the roots. All right. So this is those methods available in that nonlinear problems in order to determine the roots. Okay, bisection method. We just go step-by-step approach. What does it mean, the bisection methods? Okay, one of that bracketing method for root finding. So as we know that, all remember that the bisection method is one of the bracketing methods for in order to find the root finding. So bracketing means, so we determine that some certain guess, and then we just look into that whether is there any changing direction. All right, and then if it is direction is changed, that means there is a root. If not, then we have to choose another value. Okay, based on the theorem on the exiting roots. All right, so it's based on that theorem of exiting of the roots, and it's also required two starting point to start an iteration. All right, so remember that every time when you just initial guess, you need to find the followed by another iterative value, and then you substitute in the value into that the process, and you need to look into that whether it's converge or is in order to you can find that the roots or not. All right, so we just look into that later, the example, then you will know that the step-by-step approach in order to determine the roots. Okay, it also required the bracket to be valid. Remember that it's required the brackets to be valid. If it is invalid, that means it's not, that means the process failed. All right, we consider the process failed. So in order to fulfill the requirement, so the bracket has to be valid. And also ensure that the bracket get half in each iteration. So every time when you intended to look for that roots of that particular problems, particular non-linear equation, so you have to take that mid value. I mean half of that the value which is you look for. All right. So which means x1 plus x2, or maybe you can say that x lower value and upper value, it add up the two value and divided by 2. And then use that the approximated value, or we call that as a iterative formula or iterative formula value, and you substitute into that function, and you need to check whether the system or the process is converged or not. Okay. All right. All right. In the based on theorems, an equation, all right, an equation, as I said, is approximating the zero value. All right. When the effect is real continuous, okay, remember that is a real continuous function. Okay. If it is discontinuous, it will be not converge. Sometimes it will be slow converge. Okay. So it has to be continuous. All right. The fx function has to be continuous function. All right. So okay, and it has to at least one root between xl and xu. So what does it mean xl? Xl mean is x a lower boundary or lower value, and the xu is the upper boundary. So x is u for upper value. Okay, x upper and x lower. Okay, so this is a upper, is a lower, is a upper value. Okay, so if okay, so say that either given in a graph, all right, so you can illustrate that, say this is a graph of fx, so we just determine the two value which is upper value is determined by the xu. Okay, so this is stand for that upper value, and then the xl is determined by that indicate for that the lower value of the graph. So if you have to choose, between the two values, all right. For example, usually when we pick these two value and we substitute into this equation, all right. So you substitute in that function and we multiply the both function after you substitute lower boundaries and upper boundary, and the direction is changed, which means you give you the negative value. That means there is a root for this 2 point. There is a root between these 2 points. Okay. All right. Just remember that it's very, very important. All right. So it has to be fulfill this condition, the first condition. Okay. So if it is not, then you mean you have to choose another value. Okay. So this is, you have to check always. So as per my advice, what we can do is you must check that the next number. So say when you're approximating the zero value, so you can check the next value, which is 1. Okay, the real numbers, which is 1. All right. So you can check that the between two number, whether you can see that direction is changed or not. All right. If it is not, then maybe you can take another value. Say if you just substitute 1 here, and then you still get a positive value. So what you can do is you can choose 2. All right, take the another next value, and then you can see that whether this is fulfill this condition or not. So if it is fulfill this condition, that means there is a root between 0 and 2, and from there you can use that the iterative formula. I will show you later. So you can find the root of this bisection method. Okay, now if the function fx does not change sign, okay, that's a phase case. The first case, as you know, that fx lower value and fx upper value. Okay, so fx x upper value if less than 0, the 1. All right. Say what if it doesn't change the sign? That means it's still greater than 0. So that is a two possibility actually. Okay, there is a two possibility, which means the root may still exist between the 2 points. So if you can see that in the graph, so maybe the point that you choose, probably you choose it's this distance. All right. So maybe when you choose any initial guess, you choose maybe the graph, it will show that the positive side of it. Okay. So when you just substitute this value, they give you the positive side of it. Okay, this value. And as well, when you choose another value for the upper limit, so when you choose, you also show that the same value as positive, which is fu. Okay, so this condition is may happen. You have to be careful. All right, when you choose that the guessing point. All right, so you need to check. All right, so that's what we need to use. Sometimes you need to use this formula, the iteration formula. Okay. All right. So another possibility is maybe this could happen. All right. So there might be no root between the 2 points. So which means you can see that this condition. So when the graph, all right, so it just lies on the same side. All right. Maybe the graph width is larger than the normal graph. So for this case, previously, so this graph is just cutting through here all the way down and then just going up again. But the point that you choose is slightly distance. All right. So which means when you choose, so this second phase is still positive. But look at that. Sometimes when you choose the point, it may lie in the same region. All right. Maybe that the graph will be maybe it's a large graph. I mean. So the coefficient of that, the function, for this example, cubic function. So the coefficient, it will be larger. I mean your x cube. Okay, coefficient of x cube could be a large number. So that will be that the the distance is go higher. So when it's higher, then it will be stretched out. So when you choose that the number between one to another, so probably it may fall the same side. Okay, when you check in your fx value, is still positive. Okay, and when you substitute with the upper value and still they give you the positive value. So this also is another possibility. So which is the system doesn't work. I mean you cannot find the roots. All right, and this another scenario which is when you choose that at the point where lower of the x value, so it will also show that same value. All right, so fx, so this means is a positive. So you cannot find that, you don't fulfill the condition, which is, as I said earlier, the fx lower limit and f upper limit has to be less than 0. Okay, so these are two possibility where is usually happen when you just finding a root, so have to be careful. Okay, if the function fx change sign between the 2 points, more than one root may exist between 2 points. Okay, as you can see that here. So you can see that fx function changes sign. Okay, say this a 2 point is given. So it's a xl, this is xu, so it's a lower limit, it's an upper limit. Okay, so say if it is, this could happen if you choose is a you get that your fx lower boundaries and multiply by f upper boundary. Okay, xu, and you still get less than 2, but that is a possible. They may have the 2 root in between the 2 point that you choose. So this and this, or 2 point and more. What I mean. So this 2, 1, 2, 3. That means 2 or more points could be happen. This is another scenario. Okay, so it all depends. So that's why you shouldn't choose large numbers. Okay, just choose the next numbers. So in this method, we just usually use the iterative formula in order to determine that the shorter or maybe the lower distance of the point. Okay, now disadvantage, so drawback of this bisection method. Let's see what is the drawback of this method. First is a slow convergence. Okay, so always remember that the bisection method is considered is a low order and also is a converge very slowly. When you're just writing a programming, maybe you can use a MATLAB, you can use a C programming. You just write the coding and you try to execute the simulation in order to determine the root value. It will converge pretty much slowly compared to other high order scheme methods. Second is a cannot be used on invalid bracket, as I said earlier. So if it is a invalid bracket means if the valid give you that positive value, so the system cannot be used. It doesn't work. It has to be that less than 0. If more than 0, then it doesn't work. Next, not for discontinuous function. What does it mean, discontinuous function? All right. Okay, hyperbolic function. Okay, for example, hyperbolic function. Okay, that is a one of that discontinuous function. Okay, so that is a one of that discontinuous function. It doesn't works when it come to, okay, it doesn't works, okay, when it come to that, especially for the discontinuous function. Okay, so for example, you can see that I show the example here. So which is fx function change a sign, but the root does not exist. For example, you can see, okay, this is one of the best example. Okay, so now this is one of that discontinuous function at the point where x equal to 0. All right, the graph is just a touch at that closer to that y axis. Okay, y axis, but is not cross that the y axis. Likewise, right, the other side of that graph. Okay, okay, this graph is discontinuous when discontinuous as equal to 0. Okay, but you can measure when you just look for that, say these are your upper boundary. Okay, your upper boundary, so your xu, okay, your xu, and then you check that value here is that your lower boundary. So if you just substitute the value fxl and fxu, okay, fxu, so you still get the less than 0. But however, so this graph is discontinuous at the point when x equal to 0. So what happened? The system will be undefined. So you cannot find the root of this equation. Okay, is that clear, guys? Is that clear?
Clear.
Okay, clear. Okay, very good. All right. So remember that you have to look into that each every analysis. Okay, whether in order to find that the bisection method. All right, you have to fulfill all the conditions. Okay. Now, the keynotes is very important. What the keynote is we need to consider before you execute that bisection iterative method in order to determine the roots. Okay. Now, first, you need to see that validity of the bracket. Okay, this is the first thing. The first and foremost, you have to check the validity. The condition has to be in this form, which is your fx1, they mean the lower limit when you substitute into the function. Okay, and then you multiply with that the upper value of that you substitute into the function. It has to be less than 0. Okay, it has to be less than 0. So first, this is your first condition. So this you need to how you need to validate. Okay, so once you fulfill this condition, then you can go for the next steps. Okay, so next step, once you consider this, you need to use that the iterative formula. Okay, this we also call root finding formula. So root finding formula is they indicate XR. Okay, XR, and you must remember, as I said, you need to take that half of that the value for that between the two distance, half value of that from that the two boundaries, your lower boundary to upper boundary. Okay, so you take that value XL, which means the lower boundary, plus with the upper boundary, and then divided by 2. So this is your iterative formula in order to determine that the iterative value. Okay, iterative points in order to substitute into that function. Okay, this is the second step. Okay, next is you need to use the bisection domain. All right, this is third is a bisection domain, which is say once you just determine this value, now you need to check that value, the XR value, whether this fulfill each every condition as given. All right, so once you've done that, you need to go for again. So you need to check whether it's a fulfill that the condition or not. Okay, once we just take that the new value of that XR, so you have to check. So if that the value is you need to replace the new value for XU, the lower limit, upper limit value. Okay, upper limit value. Okay, you replace with the new iterative value based on the iterative formula, which is XR. and then you check. So the x lower limit multiplied by x upper limit, if it is less than 0, that means your new value take place by, okay, you can omit that upper value, you can take that new value of that, the iterative value, which is xr. So you can ignore, okay. Keynotes. So this is like how we need to execute that bisection method. As we know that we must know the lower value or lower value, we usually indicate as xl. So base the L is stand for the lower, and then we have to know usually it will be given in the questions. All right, any of problems, they will give you the domain. So based on the domain, we have to determine that the boundaries. So the lower boundary is given xl, and the upper boundary or the upper value is a xu. So remember that when they fulfill this condition, when you substitute into the function, the lower value and the upper value, and it has to be less than 0. Okay, it has to be less than 0, then it's a valid. Okay, otherwise if it is greater than 0, that means the algorithm is failed. Then you have to adopt other numerical method, numerical algorithm, in order to determine that root value. Okay, make sure it's must less than 0. Okay, so this is an initial condition. Okay, now so next attempt is you need to find that the new root finding formula. So this is also called iterative formula, which is xr equal to xl, which is lower boundary value plus the upper boundary value, and divided by 2. So this is we call as a iterative formula, and in order to determine that the new finding or new value, or in order to determine the roots. Okay, xr. Okay, all remember that. Next, in the bisection domain, as we know that every time when you just look for, you substitute with that xr, the new roots, you need to check with that in the formula, okay, in the condition. If it is condition is less than 0, then, okay, for example, this lower boundaries multiplied by the new finding direction or new value, which is xr. So it's after substituting the function, if it is give you the less than 0, so that means you remember that you need to update that upper value. So you need to replace with that the upper boundary value with the new roots or new iterative values, and your lower value or lower boundary stay. Stay, don't disturb this. So only change that, update the upper boundary. So if it is lower boundary and the new root value, you just multiply. If it is give you the greater than 0, then you need to stay that you keep that the upper boundary value, but you need to replace with that lower boundary value to that the new finding of the iterative value. Okay, and this is how you need to check every time when you do the iterative process. Okay, say if you are lower boundary and up and then the xr value is give you the 0 value, that means that is the roots of that function. All right, the xr consider is already converged to that the roots. Okay, now stopping criteria. So when you come to the bisection method, we do have the stopping criteria. So which mean, say the first one is invalid bracket, which mean when you just use the lower boundary value and upper boundary value and substitute into that function, if it is greater than 0, that means it's a consider is invalid. All right, invalid, that means the system is failed. So immediately the algorithm or the process will be stopped. Okay, so when is come to this condition. Okay, so that means we have to look for the other approach, other method in order to determine the roots. Okay, second stopping criteria is which means the number of iterations required reach. Say in the questions or in the requirement, you have to do like 3 iteration or 4 iteration. That's it. You don't have to go further on beyond on it. Okay, just stop at that iteration and then you conclude your answer. Okay, so it's always is bound to that the number of iteration required. Okay, you don't have to do further than that. Okay, further of that iteration, you just exactly follow as what the iterations mentioned in that questions. or unless sometimes they don't give you that this statement, this requirement. So in that case, you have to check that the stopping criteria. Okay, all right. All right, so in other words, the stopping criteria, the system will be stopped once you are at a lower limit is multiplied with that the new findings of that XR is when the yield 0. So one is equal to 0, that means so you already the system will be stopped immediately. Okay, I mean the process will be stopped immediately, and they give you that the approximated root of that the function. Okay, the next is, as I said earlier, so stopping criteria. Okay, stopping criteria you have to fulfill. So you every time you need to check with that the relative approximation error. Okay, relative approximation error. How do you need to find? You can take that, say you have the first iteration and the second iteration. Take the second iteration minus with that the first iteration and divided by the second iteration, multiplied by 100. Okay, in other words, you can say that the present value, and then subtract with the previous value, and then divided by the present value, and then multiply by 100. So you can see that how much that error is. If it is error is the relative approximation error is less than the stopping criteria, which is determined by the questions or the requirements, so then you need to stop that the iteration process. So this is the 4 elements you need to consider in the bisection method in order to stop that iteration. Okay, now we're going to step-by-step approach. What is that bisection method and how we're going to conduct that the algorithm sequentially. Okay. Okay. First step, what you need to do? The first step is iteration. You need to check the bracket, as I said earlier, right? You need to check the bracket. Okay. So the bracket it has to be whether it's a greater than 0 or less than 0. If it is greater than 0, that means it's a system is failed. If it is less than 0, then you need to continue for the second step. Okay. All right. The second step, you need to find that the XR. So as you know, right, XR, you need to calculate based on that lower limit with that upper limit divided by 2. So this is a new value in order to determine that the we rounding to that the closer point to that the exact root. Okay. All right. So you need to find that the new root. Okay, that is considered we call as a first iteration. Okay. So once we just find that XR, so that is considered your first iteration. And then once you just find this root, and then you need to take this value, and then you need to check with that the previous value, which is XL. So you see the difference, how much that the absolute error is. Step 3. Step 3, you need to use that XL and XU. Okay, again, I said that the process, you need to continue with that. You need to check whether it's less than 0 or greater than 0. If it's greater than 0, then you need to update the value, the new value. And then if it's less than 0, then you continue with the process. And step 4, yes, you need to find that again. You need to find that XR, and then you check that the relative approximate, relative true error. Okay, this is actually the second iterative onward. Okay, second iterative onward, you need to calculate that the your relative error. Okay, relative error. Okay, now as you can see here, so this is actually this is stopping criteria, as I said earlier. So your approximation error, so say your first iteration and second iteration. Say you take the second iteration value and you just it's supposed to be it's approximation error, guys. Okay, so when you just get that the second iteration's value and is minus with the first iteration value and divided by second iteration value, and you get that the value is less than the stopping criteria, which is determined, then you need to stop the iteration process. Okay, so this is repeat. If it's not, then you repeat again for the step 2. Okay, you go to step 2, and then again you go back to step 3 and go back to step 4. Again, you repeat this process until it's converged to the stopping criteria. Okay. Okay. All right. take a look at this example, guys. Take a look at this example. All right. So consider the following function given as fx equal to x cubed minus 0.165 x squared plus 3.993 times 10 power of minus 4. As you can see, this is one of the cubic function. All right. And the requirement is you need to conduct a 3 iteration. All right. You need to conduct the 3 iteration by using a bisection method. So to find that the root of x. Okay. So they given in the question will be given the lower limit. Okay, so sometimes it will be in this form. So they give you like a 0, maybe this is like a 1. So you must understand that this is your lower limit and this is your upper limit. Okay, this is your upper limit. All right. So for this case, they already give you the lower limit or lower boundary value, which is 0.0, and that your upper value is given as 0.11. Okay, so from here you already know that your boundary. So first things, all you need to do, you need to check that the condition, whether it is greater than 0, you substitute into the function. Okay, substitute this value into this function. Okay, the given function, and then you check that the validity. Okay, check the validity of the bracket, whether after you substitute this value into this function, whether it's give you greater than 0 or less than 0. That is the first condition you have to do it. Okay, so we do that this example step by step approach, and pay attention closely, and please stop me if you don't get it. Okay, guys. Okay, now as we know, this is that the given function. All right, now if you just illustrate in the form of the graph, it will be like this. Okay, but remember that you are not required to just draw a graph. Remember that. Okay, for the illustration purpose, I just show you how to track that, how to conduct that the approximation route. Okay, so as you can see here, this curve is a cut through that x-axis at this point. Okay, 0.06 something. So it cut through at this point. Okay, so now we already know that the lower value and the upper value. Okay, so lower value we know just now. How much is that? 0.01, right? Okay, so just now we know 0.0. Sorry, 0.0, 0.0, and then the upper value is how much? 0.11. So 0.11. So we already know this value. All right. So now we is somewhere it fall between here. Okay, it's far away from that the exact point where the line cut through at that y-axis. So the first point is here. Okay, XL, and then second point is somewhere here. Okay, somewhere here. Okay, it's here. So XU. Oh, now as you can see that the domain is just in between the two the point where the root is passed through. Okay, so it's here. So when we just substitute into that the function, as we know, is we will get less than 0. So we already know track that we in the right direction, and then we need to look for that the approximation root of this function. Okay, continue. So now step 1. So step 1, what all you need to do, you need to check that bracket. Okay, you need to check that bracket first. So once we just substitute that the value, as I said earlier, into that function, and we know that it is less than 0. So when you multiply this value with this, and we will get less than 0. So that means we are in the right direction. So we already like start to execute that iterative process. Okay. So remember that this is step 1 is not iterative yet. Remember guys, it's not as iterative yet. We just start that our process. Okay, it's not iteration yet. Remember, second step onward, we claim that it's iteration 1 and 2 and so on. After once we're finding use that iterative formula. Okay, so as we illustrate the graph, as I said, I show you just now, so it fall between these 2 points. Okay, fall between these 2 points. So we already know that there is a root exit between the given 2 points. Okay, remember that the red line is the actual function, and then the green line is shown as a lower guess or lower limit, and the yellow line is shown as an upper guess or upper limits. Okay, so this is how we need to classify the graph. Okay, now we go to iteration 1. Okay, now we go to iteration 1. So step 2, what all you need to do? First, we need to determine that the XR. Okay, we need to determine that XR. So the iterative formula, based on the iterative formula. All right, so how are you going to calculate? So first, as we know that the lower limit, as we know, is 0, and the upper limit, as we know, that 0.11. So the XR easily can be calculated by using that formula, which is lower limit plus that upper limit divided by 2, and we get the new XR, which is 0.055. Okay, this is your first step. Okay, first iteration step. Okay, now, so if you just look for the step 3, okay, so now you need to determine that XL and XU. Okay, so XL and XU. So what we need to do, you need to substitute that the XL value is a 0, as we know that just now. And then we have to substitute that the new iterative value, which is XR, we know the 0.55. So we substitute into that function, all right, the function, the one I showed you just now, right? Into the function, and then we determine whether it's less than 0 or greater than 0. Okay, as we know that when you just multiply the two value and we obtain that the XL and the XR is a greater than 0. What does it mean? I show you the condition just now, right? So when XL multiplied by FXL multiplied by FXR is greater than 0. So what must be stay? What must be stay? The upper limit must be stay. Okay, upper limit must be stay, and we have to replace that the new value for that lower boundary. So we update the new lower boundary to that XR. So we just no longer we're going to consider the 0 value, but we take the new value, which is XR equal to 0.55. So now it will become a new XL. Okay, new XL. And the upper limit is stay, because this condition is fulfilled when FXL and FXR is a greater than 0. So you have to keep that your upper limit. Okay, now if you illustrate in the graph, you can see easily. So we just try to move the new value, the estimated root. Just now we find out 0.055. So this is initial gas. Remember, guys, the green one is initial gas and the yellow is the initial gas. And then now the new root after you find out XR, so it will be in the blue line here. It's somehow closer to the exact root. Okay, it's come to closer to exact root. Now we need to consider this and this. Okay, we just omit this. We're no longer gonna look at this. We only consider the two boundaries between these two. Okay. Next, that is iteration 1. So now we go to iteration 2. So iteration 2, okay, so iteration 2, remember that we go to step 4. So again, we need to find that the new XR, and then we need to look for that the approximation value. Okay, the approximation value. Okay, so we need to change this. All right, now next. So once you just find out, all right, that the new XL, which is 0.055, and then your upper limit is still remain the same, which is 0.11. So you need to attempt to just look for the new XR, new findings for that the roots value. Okay, so again you need to use that XR equal to, you just take the lower limit of that value, which is 0.05, and then plus your upper limit 0.11 divided by 2, and you get the new XR, which is 0.08525. Okay, now what you all need to do, you need to determine that your relative approximation error. Okay, so relative approximation error, how you could determine? So you take that your present value, okay, this is your present value 0.0825, and then your previous value. Remember just now your previous value, what it is? Your previous value, guys? What is your previous value?
0.055.
Yeah, 0.055, and then divided by 0.0825 and multiply by 100, and you will get that. Okay, I'll take the positive. All right, you get that 33.33 percentage. Okay, you see, right, every time when you have to conduct the relative approximation test, because at least what we need to do this relative approximation error, because it will show you your direction, whether your attention to get the root value towards in the right way. Are you in the right way in order to obtaining that roots? So remember that every time when you do that test, so your approximation percentage will be reduced. Okay, if it is reduced, that means it show you that is the right direction where you approaching your exact solution. Okay, if it is getting higher, then that means you are in the wrong direction. Okay, but remember that not all the time it will happen. Sometimes, you know, the approximation error will be higher when you do the first iteration, and after that you continue the process for the second iteration, and all of a sudden it will be dropped. It's just like that. Okay, it's a numerical method. That is a phenomena. Okay, so you cannot expect every time when you do the iterative process, so that your relative approximation error will be going down. Okay, it's fluctuate because due to some floating error. Okay, due to some floating error, it fluctuate, but eventually it will be converge. Okay, so that is a two type of iterative process. Sometimes, okay, I'm sure you all learn about stationary method and non-stationary method. Okay, so non-stationary method, for example, like a conjugate gradient, general minimal residual, gradient method. Okay, so biconjugate stabilization method. Oh, this all we call a non-stationary. But when you look at that, the convergence is the convergence is unstable. So every time when you carry out that the iterative process, so that the relative approximation error it become a larger and smaller and larger smaller, and eventually it will converge to the very small number. But if you look at that stationary method, so stationary method means like a Gauss-Seidel method, SOR, SVD, okay, Jacobian. So this all we call as a stationary method. So that is a smooth convergence. Every time when you look for the approximation value or approximation relative error or relative approximation error, it will be reduce the percentage. You must remember that. This is not in your syllabus, but you must remember that the process how it is work. Okay, just additional information, guys. All right, now, so as we know now is 33%, and we can see that go to the step 3, and in order to determine that the XL and XU, and we check again. So what is that the value when you substitute your new XL and you plug into that the function, and you got this value, and you get the new XR, which is 0.0825. You substitute into the function, you multiply, you get less than 0. Okay, that means the validity of the bracket is good. I mean, it works. Okay, now, so remember that I told you just now, right? So since it's less than 0, now what we can do, you need to stay that you keep that the lower value. Okay, since it's less than 0, remember the condition. So since it's less than 0, you need to keep that the lower value. Okay, and then you need to update that the upper value. Okay, the upper value just now is 0.11, right? Now the new upper value is become a 0.0825. Okay, it's become a 0.0825. There's a new your XU, that means new upper value. Okay, all right. Now, if you illustrate in the graph, you can see that you can check that the estimated error somehow it just is now is here. Okay, and then this is your green line is a new lower value, and the yellow line is your upper value. Just now you obtain 0.11. So after once you find out, see your searching domain is become a shorter. Okay, your searching domain become a shorter. It's just in between these two domain. So you already know that the exact root is somehow between these two domain. Okay, next we go for the iteration 3. Okay, in the iteration 3, Also we call as step 4. So need to determine the new XR, okay, new XR, and then the new approximation, relative approximation error. And then again, as we know that your XL is a 0.055, and then your new XU is upper limit is at 0.0825. And then again, you need to check that using that new roots. Okay, new by using that iterative formula, which is new X, which is XR equal to, so take these two value, upper and lower boundary, and divided by 2, and it give you 0.06875. Okay, so once you obtain that, okay, as we know, the question, they only mention 3 iteration. Okay, only 3 iteration. So you don't have to go further. All right. So what all you need to do is you take that the value, which is you obtain that XR, which is 0.06875. You take, you subtract to the previous value. So previous value is you get a 0.0825, right? So when you say that the relative approximation error, and you will get the 20%. Okay. So as we know that previously we know that is a 33.33 percentage. Okay, 33.33 percentage. Now you can see that it's reduced to 20%. Now you already know that yes, we already in the right direction. So in order to obtain a solution, if you illustrate in the graph, see the graph is the searching domain is moved from year to year now. Okay, it's even become a shorter. So this is your searching domain, the new searching domain for after 1 year, you're finding the new value of that for the domain. Okay, so XR, so it's 0.06875 is fall somewhere year and year. So you just since you know they only look for the 3 iteration, you can stop that and then you can give your answer. Okay, so you already there. But if we continue, then we can get the solution. But it will take that more iteration. Okay, will give the more iteration. But remember that this is the methodological process. But when you just apply this into that computer language like C or MATLAB, okay, so you can able to find a solution within a few seconds by writing a code. Okay, the mathematical code exactly will be represented in that the C programming or MATLAB. So then it will be calculate for you very fast. Huh? Okay, now say I continue that iterative process. All right. So just now we stop at where? We stop at the iteration number 3, right? Here. Okay, third iteration. So we get that percentage error, relative approximation error is a 20%. And then previously we got a 33.33. Say we continue the iterative process, iteration 4, iteration 5, iteration 6. So you can see that, you know, it's slowly, gradually, it's just your percentage of error is reduced. Okay, percentage of your approximation error is reduced. And somehow they give you that the solution to that exact, okay, 0.0621. All right. So if you just continue even more, so even it give you that more exact solution. But we don't have to do that, because always remember we have to rely on that the stopping criteria as well. Okay, stopping criteria as well. So because we just need the desired solution, not the exact solution. In numerical method, we just only look for the desired solution. All right, is that more than enough in order to conclude our result, even the real life application? All right, so as I said earlier, if you do that exact solution method, or sometimes there is a we cannot find a solution, some due to some complex function, we cannot find a solution. But when we just adopt the numerical method, so we easily can obtain a approximation solution. Okay, you don't have to find that is a great significant level or great number of decimal, but based on the desired solution is just more than enough in order to conclude your answer. Okay, so this is your exercise. All right, I want you to just you calculate, you know, as a homework, you do it. All right, so this is also you need to conduct the 3 iteration for bisection method, and then the domain is given between the lower boundary value 0.02 and the upper boundary is given 0.08. Okay, So do it as a homework, okay? So, and then do it in the group, okay? Do it in the group and then check your answer, okay? And then check the answer. This is have to be the approximation error. It's a 17.65. So make sure you get this approximation error, okay? You cross check your analysis. You just add to follow that exact steps as what I taught you just now. All right, follow that sequence, and every time check with that your bracket validity. Okay. Any question?